Hi everyone, my name is Alberto Arenas from the University of La Rioja, and today I'm going to talk about discrete harmonic analysis related to classical orthogonal polynomials. First of all, of course, I would like to thank to the organizers for letting me the opportunity to speak in this nice conference in the lovely memory of Professor José Carlos Petronilo. Well, I'm going to start with a soft introduction to harmonic analysis. And it is usual to put the beginning in the work of Joseph Fourier on the problem of the heat diffusion. By means of separation of variables, at some point he needed to express any arbitrary function by means of a trigonometric series, where the coefficients an and bn are given by these two integrals. These claims open an interest period with some controversies regarding the validity of this equality. From the point of view of the complex exponential function, for one periodic function, we define its Fourier series, where Cn of f is the Fourier coefficient, and on its behalf, for a non-periodic function, we define not a series but a Fourier integral, where f hat is the Fourier transform. So the aim of the harmonic analysis is to study when and in what sense the Fourier series or integral converges to the function. When the complex exponential is substituted by other appropriate functions, we speak about non-trigonometric harmonic analysis. Specifically, let phi a complete and orthonormal system in the Hilbert space L2 on the interval AB with respect to the measure mu. Note that also the system could be dependent of a parameter lambda, which is called the order. The application from L2 of functions to the L2 of sequences is an isometry, and the Parseval's type identity holds. The 2 norm of the sequence of Fourier coefficients of f is equal to the 2 norm of the function. The inverse of this application is called the discrete Fourier transform. Then, depending on the point of view, we have the continuous of discrete non-trigonometric harmonic analysis. For each function in LP, we associate to it its Fourier series, and for each sequence in little LP, its discrete Fourier series. The question is in what sense each series represents the function or the sequence respectively. So typical examples of non-trigonometric systems are the Jacobi polynomials of order alpha and beta, both bigger than -1, which are orthonormal on the intervals 0 pi with respect to this measure involving the sine and the cosine. And on the other hand, the Laguerre polynomials of order alpha bigger than -1, which are orthonormal on the interval 0 infinity with respect to this measure involving a power and a negative exponential. Note, please, that both measures depend on the order. So if we want to eliminate this dependence, we can consider the Jacobi and Laguerre functions, which are the product of the respective polynomial and the square root of each measure. In this way, both systems or functions are orthonormal, of course in its respective interval, but in this time with respect to the Lebesgue measure. Well, the problem I want to focus on today is known as the transplantation problem. So let's introduce it. A Jacobi function of order -1/2 is essentially the cosine function, whereas if the order is 1/2, it is essentially the sine function. So the Jacobi function could be seen in some sense as the generalization of the usual trigonometric series, and not the only generalization. For example, there exists the Bessel function, which also generalizes the trigonometric series. Anyway, Richard Askey and Stephen Wenger note in 1966 that by means of the Marcel-Riesz inequality and the Hilbert's inequality, it's possible to prove the norm equivalence of the Fourier coefficients of this particular different order. And this is called a transplantation theorem for the usual trigonometric coefficients. Well, Askey himself extended 1 year later this result, including some potential weights, for different orders bigger or equal than -1/2, p between 1 and infinity, and a power weight with the exponent sigma between -1 and p minus 1. The weighted LP norm of the Jacobi Fourier coefficient of order alpha beta is equivalent of the respective of order gamma delta. On its behalf, he also did it for Laguerre function when the order differs in 2 units with some additional restriction in p when alpha is negative. While in 2019, Jorge Betancourt and his collaborators extended Askey's work for weights in the discrete Magenhaupt class in the special case alpha equals beta equals lambda minus 1/2, which corresponds with the so-called ultraspherical functions. We recall here that a weight W belongs to the discrete AP class if this supremum is finite, with the usual modification in the case p equals 1. The way used by Betancourt et al. Is to define the transplantation operator T lambda 1, lambda 2 in the following way. First, we obtain the discrete Fourier transform with respect to the family of order lambda 1, then calculate its Fourier coefficients with respect to the family of order lambda 2. The case lambda 1 equals lambda 2 is out of interest because the transplantation operator in this case is the discrete Fourier series, so that's why we usually omit it. Well, then they prove this weighted norm inequality for the transplantation operator for the ultraspherical case, and also the weak estimate for the case p equals 1. However, as we can see here, they need to impose, in the last case, an additional restriction in their orders. The key of the proof is to consider the transplantation operator as a Calderon-Sigmund operator, and its corresponding discrete Calderon-Sigmund theory was developed by themselves in the same paper. So as a corollary, they obtained a weighted transplantation theorem for ultraspherical coefficients for functions in the weighted LQ, where the weight V is in the usual Magenhaupt class of weights. After that, the authors extended Betancourt results to Jacobi functions of any order bigger or equal than -1/2. It was done in 2019. We also eliminate the additional condition in the case p equal 1, but however, the question for orders in the range between -1 and -1/2 is still open. As a corollary, weighted transplantation theorem for Jacobi coefficients is obtained, again for orders bigger or equal than -1/2. Well, regarding the transplantation problems for Laguerre functions, we need to introduce a discrete Markov local class of weights with the usual modification for p equals 1, which we omitted because we will not use it. But moreover, we need two more conditions on the weight that we will denote by HP and HP star. With those tools, we are in position to establish a weighted norm inequality for the transplantation operator in the Laguerre case. In this setting, the requirements for the weights depend on their relation between the orders. So let alpha and beta different and bigger than -1, p between 1 and infinity, and a weight that satisfies this equivalence and condition HP if beta is equal to alpha plus 2k, the equivalence and condition HP star if alpha is equal to beta plus 2k, and finally the weight belongs to local AP and conditions HP and HP star if the absolute value of the difference between alpha and beta is not equal to 2k. Then we obtain this weighted norm inequality for the transplantation operator. Again, the K is a discrete Calderon-Sigmund theory, but in this time we need a local variant developed by the authors. And note, please, again, that also the case P equals 1 is still open in this setting. Well, in the special case of power weight, the requirement of the weights simplifies to this condition on the exponent, where gamma here denotes the minimum of the orders. The necessity of this condition is conjectured to be true for all possible values of the orders alpha and beta, but the question is also open. We only have proved, a full characterization for the weighted norm inequality in the special case considered previously by ASCII, and the analog for the case alpha equals beta plus 2. Finally, to establish a transplantation theorem for Laguerre coefficients, we need to introduce the space of functions L1 sigma on the positive real line. We say that a function f belongs to this space if this power-weighted L1 norm is finite. We will also need to introduce these two regions of the plane space of admissible orders. The set U consists of the axis and the set V on the wall space minus U. So with this definition, let alpha and beta different and bigger than -1, p between 1 and infinity, and a power weight with exponent A, and sigma so that fulfills this condition depending on the belonging of the order to the regions V or U. If this condition holds, where gamma is again the minimum of the orders, then the power-weighted norm of the Laguerre coefficient of different orders are equivalent for functions in this weighted space. Note that in this setting, the case when the weight is a general weight on the discrete Markov class or on the discrete local Markov class is also an open problem. And I think that this is the end of that I essentially want to speak about. So thank you for your attention, and thank you again to the organizers.